So, today in this session we are going to take up problems on communication systems. So, question number 1 first we will take. So, question number 1 is, in a communication system noise is likely to affect the signal number 1 at the transmitter, number 2 in the channel, number 3 in the information source, and the last at the destination. So, here question number 1. So, we have in the communication system we have the first information signal, information. So, first information is collected. So, information is collected and then comes the process of transmission. So, this is the transmission plus here transmission with some modulation and then it is receiver. So, and here noise can enter at this stage, and before this stage also. Noise can enter anywhere in this system. So, when noise is going to affect in the communication, noise is likely to affect the signal. So, the noise will be more affecting where the signal is of the least strength. So, you see there are two places where signal is of least strength. Number 1 point at the information source. So, at the source itself the signal is very weak and thereafter it is modulated with carrier wave, amplified and transmitted. So, during transmission in the channel also noise can enter, but that will not affect too much. And the second place, when it is being received. So, at the receiving end the signal is also very weak. During this transmission in the channel the signal is attenuated, it becomes weak, and here before receiving this is also weak. So, if noise enters here then also it is going to affect. So, we have 4 options at the transmitter. So, the noise is most likely to affect not at the transmitter. So, A is not the correct option. In the channel it will not cause too much harm. In the information source, so this option is C. So, we have C option correct, and D at the destination. Now, at the destination also it may affect, but it is not clearly written that before receiving this noise enters or not. So, the correct option is the option C, where the signal is of least strength. So, the option C is the correct option. So, now come to question number 2. Indicate the false statement. Modulation is reduced to, number A option, reduce the bandwidths used, number B option, separate different transmissions, C, ensure that signal may be transmitted over long distances, D option, allow the value of practicable antennas. So, now we have to indicate the false statement. So, you see during modulation the bandwidth is not reduced, number 1. So, let us come to option 2, separate different transmissions. So, due to modulation is carried to separate different transmissions. So, different transmissions means, suppose we are using 20 to 20,000 hertz frequency for audio transmission. Suppose we are, once somebody is transmitting from one place another place. So, there are different channels through which different areas, different transmitter which is sending the same frequency range. So, if without modulation we will send this raw signal, then all will interfere, and so it will be difficult to find these individual waves. So, interference will take place. So, modulation is of course carried to separate different transmissions. So, different frequency band is allotted to them. So, option B is actually correct. So, we have to find out the wrong statement. So, A is wrong. A is wrong statement. What about C? Ensure that signal may be transmitted over long distances. You see, if the signal is modulated, then we can easily carry it to long distances. So, this option is correct. So, this is correct option. Let us see D option. Allow the value of practicable antennas. Now, in order to transmit a signal, the size of the antenna should be the order of lambda by 4. That is, let us say it is lambda order, lambda by 4 minimum size required, that means lambda. Now, if we directly transmit my signal at the signal frequency, then the size of the antenna will be very large, it will not be practicable. So, we do this modulation so that the antenna size can be reduced and can be practicable. So, option D is correct. So, we have to choose the false statement. So, the false statement is A. So, our option is A. A is the false statement. We have to take the false statement. So, question number 3 now. The acoustic channel is used for which of the following? Number A option UHF communications, B option single sideband communications, number C television communications, D person to person voice communications. So, this is conceptual questions, and already we have covered in our theory that the option will be B, that is single sided communications. UHF option A, UHF communications will be actually ultra high frequency communications, that is used for in frequency, that is used for FM frequency modulation. Acoustic channel we are using for single sideband communications, that is our basically amplitude modulation. So, in amplitude modulation we have this carrier frequency, and this is omega c minus omega signal and omega c plus omega signal. These are upper sideband and these are lower sideband. So, these sidebands are used for amplitude in amplitude modulation, used for transmitting this audio signal. So, the option is single sided. So, either I can use this signal or I can use this band. So, this is called lower sideband, this is called upper sideband. So, for audio communications we use single sided band communications, that is the option B. So, this answer will be option B. So, now question number 4. Amplitude modulation is the process of number A option superposing a low frequency on a high frequency, number B superposing a high frequency on a low frequency, number C carrier interruption, number D frequency shift and phase shift. So, here amplitude modulation we are seeing. So, in amplitude modulation we have a carrier wave AC t given by AC sin omega c t, whose amplitude is modified according to the modulating signal, that is AM sin omega mt, omega signal t, omega s. So, in amplitude modulation the amplitude of the carrier wave is modified according to this signal. So, here number A option is superimposing a low frequency. So, here the signal is a low frequency and this is a high frequency. So, we superimpose the amplitude of the carrier wave is modified according to this signal, modulating signal, that is signal wave. So, this process is number A option, superposing a low frequency on a high frequency is correct option. So, A is correct option. Let us see what about B, superimposing a high frequency on a low frequency. We cannot superimpose a high signal wave to a low carrier wave. So, this is not done in amplitude modulation. Now, carrier interruption is also not done, and D option, frequency shift and phase shift, this is not done in amplitude modulation, they are done in frequency modulation and phase shift modulation. So, here the option A, answer A is the correct option. So, question number 5th now. A carrier is simultaneously modulated by two sine waves with modulating indices 0.3 and 0.4. The total modulation index is number A option 1, number B cannot be calculated unless the phase relations are known, number C 0.5 and D 0.7. So, now let us develop first the expression if there are many modulating signals. So, let V1, V2, V3 dot dot be different simultaneously modulating signals, signal voltages. So, these are instantaneous values. So, this is now the signal is not a single voltage, there are different voltage waveforms of V1, V2, V3 values. The total modulating voltage is given by Vt. So, Vt is the RMS value of this, that will be V1 square plus V2 square plus V3 square plus dot dot. Now, let us find the modulating index, that is Vt by Vc is equal to root over V1 square by Vc square plus V2 by Vc whole square plus dot dot dot. This is total modulation index, that comes out to be modulation index of first plus modulation index of second square, like this. So, this is the expression for the total modulation index if there are simultaneously acting different signals of modulating index M1, M2, M3, like that. Now, in our problem it is given that there are two signals of modulating index M1 is equal to 0.3 and M2 is equal to 0.4. So, we have to calculate the total modulation index. So, this modulation index is 0.3 whole square plus 0.4 whole square, that is, this is 0.09 plus 0.6, that is 0.16, that is 0.25, that is equal to 0.5. So, the total modulation MT index is given as 0.5, which is option number C. So, here answer is option number C. So, now question number 6. So, amplitude modulation is used for broadcasting because option A, it is more noise immune than other modulation system. Option B, compared with other systems it requires less transmitting power. Option C, its use avoids receiver complexity. Option D, no other modulation system can provide the necessary bandwidth for high fidelity. So, here in amplitude modulation, the amplitude modulation is the preferred over the frequency modulation because of the less complexity in the receiving end. The receivers use are less costly compared to frequency modulation. So, option C is the correct answer. Correct answer is option C. About other options, suppose I take option A, it is more noise immune than other modulation system. So, this is not, that is, so the noise may enter here also and others also, since it is more immune, so it cannot be used. So, noise is not desirous. So, option A is wrong. Compared with other systems, it requires less transmitting power. This is wrong option. D option, no other modulation system can provide the necessary bandwidth for high fidelity. So, this is also not the correct option. So, correct option is because it avoids receiver complexity. It is easy to operate, less costly at the receiving end. So, question number 7 now. Frequencies in the UHF range, ultra high frequency range, normally propagate by means of option A, ground waves, option B, sky waves, option C, surface waves, option D, space waves. So, here option D is correct, space waves, because you see earth, this is earth, and earth is surrounded by a ionospheric layer. So, when we send a wave from here earth station, then this wave is reflected for radio waves. For radio waves, this wave is reflected because this frequency matches with the frequency of these dipole oscillations. So, this layer, ionospheric layer, forms a dipole, and we call that this dipole actually oscillates. So, when the wave, incident wave, here the wave incident matches with this, or it has a less frequency, it is reflected. If it matches with the plasma oscillation or dipole oscillation frequency, then it is absorbed, and if this is high, then it is transmitted. So, what happens? Ultra high frequency UHF range, they have a very high frequency. So, then generally they get transmitted from these ionosphere. So, for these waves to be transmitted over large range, we use space waves propagation. So, the option D is the correct answer. Answer is option D. Question number 8 now. The absorption of radio waves by the atmosphere depends on number A option, their frequencies, option B, their distance from the transmitter, option C, the polarization of the wave, option D, the polarization of the atmosphere. Now, the absorption of radio waves by the atmosphere. So, you see, already we have seen in the previous question that we have a ionospheric layer which due to cosmic radiations from external radiations, solar radiations, cosmic radiations get ionized and forms a dipole layer. So, when a positive and negative charge, a dipole layer is formed, then this dipole oscillates, and there we call that frequency as the frequency that this plasma layer is formed. So, dipole layer is also called plasma layer. So, this is plasma frequency. So, now the radio waves, if incident from the earth station, will get absorbed if this frequency matches with this frequency. So, number A option, if their frequency matches, then they will be absorbed. Now, the distance of the transmitter does not matter, the polarization of the wave also does not matter. The D option, the polarization of the atmosphere, you see atmosphere cannot be polarized. So, that is a meaningless option. So, we have the correct option as option A. So, the radio waves whose frequency matches with this plasma frequency, the dipole layer which oscillates, and the frequency by which that oscillates, that is called plasma frequency. So, option A. Question number 9 now. A 100 volt carrier is made to vary between 160 volt and 40 volt by the signal. What is the modulation factor? Option A 0.3, option B 0.5, option C 0.6, option D none of these. Now, we have been given this V of this carrier wave as 100 volts, 100 volts. We have V max as 160 volts and V minimum as we have 40 volts, 40 volts. We have to calculate the modulation index. Now, V max will be given as Vc 1 plus m modulation index and V min will be given as Vc 1 minus m, where m is the modulation index. So, V max already given as 160 and Vc is given as 100, 1 plus m. So, here 1, so this is 1.6 is equal to 1 plus m, implies m is equal to 0.6 modulation index. You can see from here also V min is given as 40 volt is equal to Vc 100 volt 1 minus m. So, this is 0.4, 0.4 is equal to 1 minus m. So, m is equal to 1 minus 0.4 is equal to 0.6, which has the same value. So, the option 0.6 is C option. So, we have answer as option C. So, question number 10 now. A carrier wave with an amplitude 140 volt is modulated by a signal with an amplitude of 80 volts. What is the amplitude of the lower sideband frequency? Option A 80 volt, option B 60 volt, option C 40 volt, option D 20 volts. So, here we have the carrier wave frequency as 140 volts. We have the modulated V modulation is equal to 80 volts and we have to calculate V min, the minimum, how much minimum voltage will be there. So, you see here, let us recall the graph of modulated. So, you see here this graph will be like this. So, this is the just the envelope of this modulated wave. So, here we have this is Vc and this is V min and this is V max. So, V min, V minimum is given by AC, that is here the amplitude of the carrier wave 1 minus modulation index, and V max is given as AC amp 1 plus m. So, here first of all let us calculate m, modulating index, that is the modulating signal by this carrier wave voltage amplitude. So, modulating signal voltage is 80 by carrier wave is 140. So, we have now 4 by 7. So, modulation index is 4 by 7. So, we have to calculate the minimum. So, V min will be equal to AC, that is the amplitude of the carrier wave, that is 140 into 1 minus 4 by 7, that is equal to 140 into 7 minus 4, that is 3 by 7. 7 into 20, that will be 3 into 2, 60 volts. So, this V minimum is 60 volts. So, 60 volts is the option B. So, we have the option as option B. So, question number 11 now. The maximum peak to peak voltage of an AM wave is 16 millivolts, while the minimum peak to peak voltage is 4 millivolt. The percentage modulation is 30%, option A, option B 40%, option C 50%, option D 60%. So, now you see here this is the envelope of this modulated wave. So, here we have in the problem it is given that peak to peak voltage is 16 volt. So, from here to here we have 16 millivolts, and then the peak to peak minimum is 4 millivolt. So, this is 4 millivolt. So, this. So, we have here V max is equal to 16 by 2, that is 8 millivolts, and V minimum is equal to 4 by 2, that is 2 millivolts. So, here we have to calculate the percentage modulation. So, the percentage modulation, we know the formula is given as this V max minus V min by V max plus V min. So, this modulation index here is M, V max is 8 minus 2 millivolts by V max 8 plus 2, that is 6 by 10 modulation index. So, in terms of percentage this will be 60%. So, modulation index is 0.6 and in terms of percentage into 100, that is 60%, that is option D. This is option D. So, now come to question number 12. In AM wave the modulation index is M. The fraction of the total power contained by the sideband is given by option A m square by m square plus 2, option B m square by 1 plus m square, option C m by 2 plus m, option D m square by 1 plus 2 m square. So, now the power of the carrier wave. Now, the power is of a sinusoidal is given by P is equal to I square R. So, or in terms of I, or in terms of V is V square by R. So, here suppose EC is the carrier wave amplitude. So, we have EC by root 2 whole square by R. So, you see we have to use the RMS voltage, and RMS voltage is the peak voltage by root 2. So, we have to use RMS. So, keep in mind that the RMS voltage for a sinusoidal voltage is the 1 by root 2 times its amplitude. So, suppose EC is the carrier wave amplitude. So, this EC by root 2 is the RMS value. So, RMS voltage square by R. So, this is the power contained by the carrier wave. Now, power in the side bands is equal to, now power in the side bands, there are two side bands, lower side bands and upper side band, and again the RMS value. So, the modulation index into EC by 2 is the amplitude of this side bands. So, this again root 2 times whole square by R, and this is one side band, suppose I say lower side band, and again for upper side band it will have 2 root 2 whole square by R, where M is the modulation index. So, we will simplify it. This comes out to be equal to this M square EC square by 2 into 2 4 into 2 8 R, and this is this again same. So, by 2 this is 2 times. So, this will be 2 into this, that is 4 R. So, we will have 4 R here. So, this is the power in the side bands. Now, total power P total is equal to carrier wave, that is EC square by this root 2 means 2 R. So, the power in the carrier wave, that is EC square by 2R plus sideband powers, that is m square EC square by 4R. So, let us take common, that is EC square by 4R. So, if I take common EC square by 4R, then here we will get 2 plus we will get m square. So, this is the total power in the total power associated with the modulated wave. Now, we have to find the fraction of the power in the sidebands, that is we have to find eta, the fraction, that is power in the sidebands by the total power. So, power in the sidebands is m square EC square by 4R upon this thing, that is EC square by 4R 2 plus m square. So, EC square by 4R, EC square by 4R. So, we have m square by 2 plus m square. So, we have this as the first option. So, here the answer is the first option. So, question number 13 now. A radio can tune into any station in the 7.5 megahertz to 12 megahertz band. What is the corresponding wavelength band? So, here we have the frequency range from 7.5 megahertz to 12 megahertz. So, we want the corresponding wavelength. So, we use the expression V is equal to n lambda, we want lambda. So, implies lambda is equal to V by n. So, let us see first lambda for 7.5. So, lambda 1 is equal to velocity of this electromagnetic waves is 3 to the power 8 meter per second upon this frequency, that is 7.5 megahertz. This is 10 to the power 6 megahertz. That is here 3 and this into 100 by 7.5. So, suppose 30 into 10 by we have 7.5. So, this comes 4. So, this is 40 meters. So, we have 40 meters for this 7.5 megahertz, and let us see for 12. So, lambda 2 is 3 into 10 to the power 8 meter per second. This is in hertz, 7.5 megahertz. So, 3 into 10 to the power 8 by 12 hertz. So, we have now 3 into 10 to the power 8 12 megahertz, that is 10 to the power 6 into 10 to the power 6 hertz. So, this is 300 by 12. This is 300 by 12, that comes out to be something 25 meters. So, we have the range from 25 meters to 40 meters, that is option number A. So, the answer is option number A. Come to question number 14 now. Which of the 4 alternatives is not correct? We need modulation. So, for the modulation, which of these 4 options is not the correct? So, option number A, to increase the selectivity. Option B, to reduce the time lag between transmission and reception of the information signal. Option C, to reduce the size of antenna. Option D, to reduce the fractional bandwidth, that is the ratio of the signal bandwidth to the center frequency. So, now in this question we have 4 options for which we require that which is not required for modulation. So, option B is here the correct option. Let us see why. So, option B tells to reduce the time lag between transmission and reception of the information. So, we do not do modulation to reduce the time lag between the transmission and the reception. This is not the cause for which we do this modulation. Now, modulation is carried out to reduce the size of antenna, because if we transmit the baseband signal, the direct signal, the raw data, then the size of antenna will be large. So, of course, we do modulation to reduce the size of the antenna. D option, to reduce the fractional bandwidth, that is the ratio of the signal bandwidth to the center of the frequency. Of course, modulation is required to reduce the fractional bandwidth. So, D is also the need for modulation. So, what is not required in modulation is the option B. It does not reduce the time lag, it is not used to reduce the time lag between transmission and the reception. So, question number 15 now. If a carrier wave of 1000 hertz is to carry the signal, the length of the transmitting antenna will be equal to. So, in this problem, let us see first what is the wavelength of the signal wave. So, V is equal to n lambda, implies lambda is equal to V by n. So, lambda we require is velocity of electromagnetic wave is 3 into 10 to the power 8 meter per second, and we have been given 1000, that is 10 to the power 3 hertz. So, we have lambda is equal to 3 into this is 10 to the power 5 meter, that will be something 300, this to 300 kilometer. So, the lambda required will be 300 kilometer. Now, this is lambda. So, the minimum size of L minimum size is the order of lambda by 4. So, by 4 is 75 kilometer. So, you see this, the minimum size of antenna requires 75 kilometer if 1000 hertz frequency has to be directly transmitted. So, 75 kilometer is the option C. So, we have option C as the answer. So, now question number 16, the maximum distance between the transmitting and receiving TV towers is 72 kilometer. If the ratio of the heights of the TV transmitting tower to receiving tower is 16:25, the heights of the transmitting and receiving towers are, radius of earth is 6400 kilometer. Option A 25 meter and 75 meter. Option B 80 meter and 125 meter. Option C 40 meter and 80 meter. Option D 51.2 meter and 80 meters. So, now this is earth and we have two different towers of different height, suppose H1 and this is H2. So, this is H1 and you just see this is H2, this is H2. So, you see this is, suppose here to here this distance is R1 and here to here distance is R2. So, the total range R1 plus R2 is given as R1 plus R2 is given as 72 kilometer, that is equation number 1, and it is given that H1 by H2 is equal to 16 by 25, this is equation 2. What we have to calculate, what is the height H1 and H2? We have to calculate H1 and what is H2, we have to calculate. So, now we use the expression that the range of a tower, is given as R is root over 2 height H into radius of earth. This is the expression for the range covered by a tower. So, this R1 will become 2 height H1 into radius of earth RE plus root over 2 h2 radius of earth RE, that is equal to 72 kilometers. Now, this radius of earth value is given as 6400 kilometers. So, root RE will become 80. So, root 2 times 80 if I take common, then it will be root h1 plus root h2 is equal to 72. So, you see root h1 plus root h2 will be this 72 if I take it 8. So, it is 9 by 10 root 2. This is equation number 3. We have to simplify. So, from this h1 by h2 is this. So, we have root h1 by root 2 h2 will be, so we will have from here we will have root h1 upon root h2 will be 4 by 5. So, let us put this. So, we have root h1 plus root h2. Root h2 is 5 by 4, root h1 9 by 10 into root 2. So, this is again 1 plus 5 by 4 is 9 by 4 root h1 is 9 by 10 root 2. So, this 9 goes off, this root h1 becomes 4 by 10 root 2, implies h1 becomes 16 by this 10 becomes 100 into 2, that is 8 by 100 is 0.08 kilometers, that is 80 meters. So, we got h1 as 80 meters. So, you see h1 by h2, we have h1 by h2 as 16 by 25 implies h2 is equal to 25 by 16 into 80. This comes to be 5 and this is 125 meters. So, we have finally we have h1 as equal to 80 meters and h2 is equal to 125 meters, this combination. So, 125 and 80 is option B. So, the correct answer is answer B, that is 80 and 125 meter. So, now question number 17. Radio waves used for radio broadcast which are in the frequency range, option A 10 kilohertz to 20 kilohertz, option B 2 megahertz to 10 megahertz, option C 50 megahertz to 100 megahertz, option D 200 megahertz to 500 megahertz. So, here option B is the correct, which is from 2 megahertz to 10 megahertz. This option 2 is correct, this is used for radio broadcast. So, for this question this answer is option B, that is from 2 megahertz to this 10 megahertz, 2 megahertz to 10 megahertz. This is used for radio communication. So, question number 18 now, which of the following frequencies will be suitable for beyond the horizon communication using sky waves? Option A 10 kilohertz, option B 10 megahertz, option C 1 gigahertz, option D none of these. So, the option B is the correct here, 10 megahertz. So, here answer is option B, that is 10 megahertz. So, with this frequency what happens, this ionosphere can transmit these frequencies very well. So, you see this is our earth and this is the ionosphere medium. So, when we send this frequency, then this ionosphere can transmit this signal very well. Lower than this frequency will be absorbed and still lower than this will be reflected as radio waves. as reflected. So, radio waves has a frequency less than this, so they are reflected. So, waves with frequency larger than 10 megahertz will be easily pass through the ionosphere. So, space wave propagation, that is beyond the horizon communication, is used for this.